Hi everyone, and welcome to another episode of Synthesis Workshop. In today's installment of our Advanced Organic Chemistry course, we are joined by Julia Reisenbauer. Julia has previously given a talk on this channel discussing the diversification of indole skeletons through nitrogen atom insertion, which I strongly encourage you to check out. I'll briefly reintroduce her now. Julia earned both her bachelor's and master's degrees at ETH Zurich, where she later also pursued her PhD. She completed her master's degree in the Carrera group and her doctoral studies in the Morandi group. There she's been working on transfer hydrogenation reactions and nitrogen atom insertion into indole scaffolds. Right now, she's pursuing a postdoc in the field of biocatalysis in the group of Francis Arnold at Caltech. Today, Julia will continue our synthesis module with her presentation on reversible reactions in catalysis and synthesis. And with that, I'll hand it over to you, Julia. Thank you for joining us.
Thank you, Kathleen, for your kind introduction and for giving me the opportunity to hold this lecture. Today we are going to discuss reversible reactions in the context of catalysis and how they can be utilized synthetically. First, I want to briefly highlight the key differences between irreversible and reversible reactions. Often, irreversible reactions are performed to access more complex molecules. One classical example is the coupling of acyl chlorides with amines to give amide products. Also, in classical catalytic reactions, high-energy starting materials are usually employed to drive the reaction towards the desired product formation. This showcases that in irreversible reactions, more reactive starting materials are used and more stable products are formed, making these reactions exothermic in nature. On the other hand, reversible reactions are ergoneutral or nearly ergoneutral, as both the starting material and product exhibit similar or the same energy. As a subset of reversible reactions, isofunctional reactions can be defined in which both the starting materials and the product exhibit the same functional groups, and product mixtures are usually obtained, as shown here for the ester metathesis reaction. If catalysts are necessary to facilitate a desired reversible reaction, the same catalytic system can facilitate both the forward and reverse reaction. To drive the equilibrium to one side, so to favor either the forward or reverse reaction, driving forces must be implemented, for instance based on Le Chatelier's principle. This aspect will be discussed in more detail later. In the last decades, reversible reactions found application in various fields, ranging from synthetic organic chemistry and dynamic combinatorial chemistry to material synthesis. With the implementation of reversible reactions, a few challenges need to be overcome to utilize these for various synthetic purposes. As previously mentioned, especially in isofunctional reactions, usually a mixture of product and starting material are obtained, and thus driving forces need to be implemented to shift the equilibrium of the reaction. For instance, in bimolecular reaction, one starting material can be added in excess with respect to the second starting material, and thus the reaction is driven towards product formation. Also, using starting materials that exhibit a ring strain release upon reaction or the formation of volatile or insoluble products or byproducts may drive the reaction towards the desired site. At the same time, when novel reversible reactions are developed, the reversibility of all elementary steps need to be ensured. Thus, thermodynamic sinks, for instance due to the formation of energetically low-lying intermediates, need to be avoided. On this slide you can find a non-exhaustive list of classical examples of reversible reactions enabling the formation of reversible covalent bonds under thermodynamic control. These reactions have been of long-standing interest, especially to access self-assembled, complex supramolecular systems. Functional groups involving carbonyl units have been of special interest since they may undergo various transformations. In particular, the condensation to access imine-type compounds under mild conditions have sparked the development of numerous applications and have been used in combinatorial chemistry settings, for instance. Besides carbonyl functionalities, also the reversible exchange of alcohols in borate esters or thiols in disulfides have been demonstrated to be synthetically useful. Besides these classical reversible transformations, a plethora of other reversible reactions have been developed and shown to be synthetically useful. Some of these will be discussed in the following. A prominent example of a reversible catalytic reaction is the transfer hydrogenation reaction. Transfer hydrogenation reactions refer to the transfer of hydrogen to an acceptor molecule from a donor molecule, usually mediated by a catalyst. It is an attractive alternative to direct hydrogenation as no hazardous pressurized hydrogen gas is required, nor an elaborate experimental setup is needed. Also, the hydrogen donors and usually involved catalysts are readily available, inexpensive and easy to handle, and the major side product can often be recycled. Depending on whether the oxidation of an alcohol or the reduction of a carbonyl is the desired reaction, two name reactions have been developed, namely the Oppenauer oxidation and the Meerwein-Pondorf-Worley reduction, both relying on the use of Lewis acids as catalysts. To facilitate the oxidation of alcohols via a transfer hydrogenation reaction, usually an excess of a hydrogen acceptor molecule, for instance 1,1,1-trifluoroacetone as shown in this example here, is employed. On the other hand, the reduction of a carbonyl moiety can be mediated if an excess of the hydrogen donor reagent, for instance isopropanol, is used. Over the decades, it was also shown that the transfer hydrogenation can be mediated by late transition metal catalysts involving first, second, and third row transition metals of groups 8, 9, 10, and 11. In the early 1980s, the first reports of the ruthenium-catalyzed asymmetric transfer hydrogenation emerged, and since then this field of research has received significant attention. Asymmetric hydrogenation is an important process in the fragrance and pharmaceutical industries for the reduction of various unsaturated substrates to excess chiral compounds, culminating with the seminal work by Kagan and the award of the Nobel Prize to Noori and Knowles for their contributions in the field in 2001. As discussed, transfer hydrogenation reactions play a key role in synthetic organic chemistry. In recent years, increasing interest in developing transfer reactions transferring groups other than hydrogen has emerged. Often these reactions rely on the implementation of a catalytic system that enables the transfer of a functional group from a donor to an acceptor molecule. In general, these transformations are often summarized as shuttle catalysis reactions. The development of these transformations is especially useful if they can circumvent the use of highly hazardous and extremely reactive reagents. At the same time, novel reactivities have been discovered based on this reaction principle, as both functionalization as well as defunctionalization strategies are accessible using similar reaction conditions. Going beyond transfer hydrogenation reactions, a variety of other reactions were developed in recent years based on the shuttle catalysis concept. A selection of these is presented here, mainly focusing on the implementation of homogeneous catalysts. Some of these reactions will now be discussed in more detail. Nitriles are key functional groups in organic chemistry, as they can be found in a variety of bioactive compounds and represent versatile intermediates as they can be transformed into a plethora of other functional groups. A practical and atom-economical method for the preparation of nitriles is dehydrogenation, which enables the access of nitriles from readily available alkene precursors. However, the prerequisite for toxic HCN gas or other similarly hazardous surrogates, such as acetone cyanohydrin, has hampered the use and development of this reaction on laboratory scales. In 2016, the Morani group reported the use of a simple, markedly less toxic aliphatic nitrile as a HCN donor in a shuttle catalysis process. Under nickel and Lewis acid co-catalysis, isovaleronitril proved to be an efficient HCN donor to access hydrocyanation products from the corresponding alkene and alkyne starting materials. The forward reaction is enabled by using an excess of the HCN donor while at the same time forming isobutene as a volatile byproduct, shifting the equilibrium of the reaction towards the right side. The authors could show that due to the intrinsic reversibility of the overall reaction, the dehydrogenation of aliphatic nitriles could also be achieved under the same catalytic system using norbornene or norbonadiene as the sacrificial HCN acceptor molecule. To drive the equilibrium towards the defunctionalization, the ring strain release upon the transfer of HCN to norbornene was exploited. An early example of shuttle catalysis was reported by the Yoon group in 1999. They discovered that a dual catalytic system composed of the rhodium-based Wilkinson catalyst, depicted here, and 2-amino-3-picoline as ligand, enabled the transfer hydroacylation from ketones to alkenes. A notable feature of this reaction is that it proceeds through a rare activation of an unstrained CC bond. Initially, condensation of the picoline-based ligand and the ketone substrate directs the rhodium catalyst towards the oxidative addition into the CC bond, enabling the overall transformation. To favor product formation, an excess of alkene is typically employed, besides the polymerization of the styrene byproduct as a driving force suggested by the authors. Related to the hydroacylation is the hydroformylation reaction, which is widely employed particularly in industrial applications. Usually a hazardous gaseous mixture of hydrogen and carbon monoxide or alternatives such as formaldehyde and carbon dioxide are necessary. A transfer process would be highly desirable as the toxic and flammable hydrogen-carbon monoxide mixture could be substituted with a relatively benign aldehyde. The forward reaction was established by the Brocards group. The reverse process was more recently developed by Zhang and co-workers, transforming aldehydes into the corresponding alkenes. Again, the addition of the hydrogen and CO functionalities from the starting material to norbornene or norbonadiene drives the defunctionalization reaction. Similarly, in classical wrapper-type chemistry, carbon monoxide and nucleophiles are employed to react with alkenes or alkynes to avoid the corresponding carbonyl compounds. Even though this process is widely applied in industry, it is rarely used on laboratory scales as pressurized and toxic CO is required. At the same time, the implementation of different nucleophiles would usually require different catalytic systems. To overcome some of these challenges and to develop a more general protocol, Morandi and co-workers developed a hydrochlorocarbonylation reaction enabling the transfer of HCl and CO. The use of butyryl chloride as a HCl-CO donor facilitated the hydrochlorocarbonylation of alkenes. The formation of propene as a byproduct serves as a driving force. The generated acid chloride products could then directly be transformed into a range of different products using various nucleophiles. The defunctionalization of aliphatic acid chlorides was also showcased using norbornene as the sacrificial acceptor molecule. Another class of isofunctional reactions besides shuttle catalysis are metathesis reactions. While in shuttle catalysis a functional handle is transferred from a donor to an acceptor molecule, in a metathesis reaction, two chemical moieties are interchanged between two reactants. In contrast to shuttle catalysis, in metathesis reaction, no clear donor or acceptor molecule can be identified, and the number and type of bonds remain constant for all the reaction partners throughout the reaction. One classical example of metathesis reaction is the alkene metathesis. Due to its broad functional group tolerance and recent achievements in catalyst activities and selectivities, it found widespread application in organic and polymer synthesis, the valorization of biomass, and in dynamic combinatorial chemistry. The Nobel Prize in Chemistry was awarded to Chauvin, Grubbs and Schrock in 2005 due to their key contributions in developing metathesis methods. To showcase the reaction's applicability, for instance in total synthesis settings, I chose to present here the successful implementation of an olefin metathesis reaction as a strategy to forge the 16-membered core ring of epothelone A and its analogues, relying on the ruthenium-based Krebs catalyst. The ring-closing metathesis is driven by the formation of ethylene as a volatile byproduct. Also, Schrock-type catalysts have been developed for alkene metathesis reactions, for instance to access polymers using norbornadiene building blocks. The ring-opening metathesis polymerization reaction, or short ROMP, shown here is driven by the ring strain release of the starting material. Besides alkenes, also imines, nitriles, and alkynes have been shown to undergo metathesis reactions mediated by different catalysts. Related to the olefin metathesis reaction, the carbonyl-alkene metathesis enables the interchange of a CO double bond and CC double bond. The earliest strategies to facilitate this transformation relied on stepwise approaches. In 1963, Scharf and Korte developed a Paterno-Büchi reaction to access an intermediate oxetane, which was then fragmented under thermal, acidic, or electron transfer conditions to yield the carbonyl-olefin metathesis products. Alternatively, metal alkylidenes were also shown to mediate carbonyl-alkene metathesis reactions. However, attempts to turn these reactions catalytic have remained unsuccessful. Another strategy relied on the implementation of alpha-beta unsaturated ketones to yield polyconjugated polymers upon reaction with tungsten-based reagents. More recently, supramolecular strategies and photocatalysts were also shown to facilitate the stepwise carbonyl-olefin metathesis approach by the initial formation of a carbon-carbon bond and subsequent fragmentation. The first catalytic approach for the direct carbonyl-olefin metathesis was realized by Lombard in 2012 based on an organocatalytic approach. The hydrazine-based catalyst is proposed to engage with the carbonyl and the alkene in a 3+2 cycle addition to initiate the overall transformation. An alternative catalytic approach for the carbonyl-olefin metathesis takes advantage of Lewis acids to activate carbonyl groups to undergo a 2+2 cycle addition with olefins, forming oxetane intermediates. These intermediates are prone to undergo a retro 2+2 cycle addition upon Lewis acid activation to afford the metathesis products. Compared to the classical olefin metathesis, the development of a CC single bond metathesis proved to be more challenging due to the inherent inertness of the unpolarized CC single bond. Common strategies to achieve this transformation have relied on the release of ring strain, cleavage of 1,3-diketones, or through intramolecular chelation. To circumvent some of the challenges associated with breaking CC single bonds, the groups of Goldman and Brookhart developed a tandem approach relying on a transfer hydrogenation in combination with an alkene metathesis. In this iridium-molybdenum co-catalyzed process, the CC single bond is transformed into a CC double bond by transfer hydrogenation, and exchange of the substituents can be easily induced by an alkene metathesis. This leads to the formation of new alkene intermediates, which after hydrogenation afford the alkane products. It should be noted, though, that there is no control over this reaction, that a complex mixture of linear alkanes is obtained. More recently, the Zhang group reported the intermolecular metathesis of unstrained CsP2-CsP2 single bonds. Assisted by directing groups, unstrained homo-bi-aryl compounds undergo aryl exchange to generate cross-bi-aryl products under ruthenium catalysis. In this context, also the CC-CH metathesis of propargyl amines and terminal alkynes as a single bond metathesis strategy was developed by the group of Zhang in 1963. The lanthanide catalyst is proposed to deprotonate the secondary amine and facilitate a beta-alkenyl elimination to form this proposed key intermediate depicted here. The alkynyl ligand can then undergo an exchange and insertion of the alkynyl moiety across the imine, and ligand exchange releases the desired product. Related to the aliphatic CC bond metathesis, the carbon-nitrogen single bond metathesis of tertiary amides mediated by a zirconium catalyst was reported by the groups of Gellman and Stahl in 2009. Similarly, amines can also be considered as alkylating sources when employed in CN and H bond metathesis reaction. Early work by Consiglio demonstrated that secondary amines can be obtained from primary amines, forming ammonia as a byproduct under ruthenium catalysis. Based on this strategy, the Bella group could show that anilines can be effectively alkylated with primary amines using the Schwarz ruthenium catalyst. Again, the formation of ammonia as a byproduct proved to be a driving force of the reaction. A limitation of the work by the group of Bella was the requirement for one of the amines to be unable to undergo dehydrogenation. For example, an aniline or tertiary alkyl amine needed to be implemented. This minimizes the possibility of side reactions occurring, but narrows the scope of the method. However, the group of Williams found that using an iridium-based catalyst, aliphatic amines could be selectively alkylated with diisopropylamine to afford N-alkyl and isopropyl amines. The CsP2 phosphorus bond metathesis has recently been developed by the Morandi group. Initial studies examined the cross-metathesis of triphenylphosphine with various aryl phosphines. A catalytic mixture of palladium-2 DBA3 and iodobenzene was used to generate the aryl palladium halide required to facilitate the aryl group exchange. This reaction yields a mixture of phosphines, and in all cases a nearly identical distribution of products was obtained for the forward and reverse reaction. Simultaneously, the group of Catani and Tobisu also reported a palladium-catalyzed CsP2 phosphorus ring closing metathesis for the formation of phosphorus heterocycles from bisphosphines. In contrast to the work of Morandi and co-workers, a chelation-assisted CsP2 phosphorus oxidative addition was proposed as the addition of aryl iodide to form phosphonium intermediates was not necessary. The groups of Catani and Tobisu have also developed another route to phosphol derivatives by a CsP2 phosphorus CsP2H ring closing metathesis. In contrast to the other work, this reaction required a monophosphine as a starting material, and benzene was formed as the only byproduct. Based on mechanistic work, a catalytic cycle was proposed wherein the palladium catalyst undergoes cyclometallation, followed by reductive elimination to give a neutral palladium species and a phosphonium intermediate. This can then undergo oxidative addition to form an intermediate palladium complex. Reaction with acetic acid is proposed to release the phosphol product and regenerate the palladium catalyst. Both CO and CS metathesis reactions have been developed. Classical examples are, for instance, the transesterification or transacetalization, and related the thioester as well as thioacetal and disulfide exchange. By contrast, processes invoking substituent exchange of ethers are considerably less prevalent. Progress in the field was made by the group of Morandi. They found that Lewis acidic iron 3 triflate could promote the cyclization of diethers to form cyclic ethers through a ring-closing CsP3O metathesis. Although gaseous dimethyl ether is formed as the byproduct, the authors found that it is not necessarily the driving force of the reaction. In addition, attempts to perform the ring-opening metathesis of tetrahydropurane through reaction with dibutyl ether were unsuccessful. Based on further mechanistic studies, a mechanism was proposed wherein one ether is activated by the Lewis acid and the other ether can thus attack to form a cyclic oxonium species. The product is consequently formed by the attack of a putative iron methoxide species. The same group also developed a metathesis reaction involving aromatic thioethers, enabling the exchange of aryl substituents, complementary to cross-coupling strategies to access these motifs. They developed a CsP2s-SH metathesis reaction using a palladium precatalyst with lithium HMDS used to generate a thiolate in situ. An excess of the thiol was required, and it is proposed that the poor solubility of the lithium thiomethoxide byproduct provides a sufficient driving force to favor formation of the products. Further development of this reaction using nickel catalysis also led them to develop a macrocyclization strategy based on the same CS-SH metathesis principle to access thioethers. There are numerous early examples of C-silicon metathesis reactions, mainly for the preparation of organosilane. For example, it was demonstrated that trisilocyclohexane, a 4-tetrasiloadamantane, using aluminum tribromide when heating. Extrusion of the volatile tetramethylsilane byproduct likely provides a driving force for this reaction. Another interesting strategy circumventing the poor product selectivity, often affiliated in alkene metathesis reactions, was developed by the group of Wakatsuki. By using a ruthenium-based catalyst, a carbon-silicon carbon-hydrogen bond metathesis between vinyl silanes and monosubstituted alkenes was realized. This reaction is driven by the release of ethylene and gives vinyl silanes. Mechanistic studies suggested that a ruthenium hydride undergoes a hydrometallation with the vinyl silane. At this stage, beta-silicon elimination occurs to give a ruthenium silyl complex and ethylene. Silyl metallation of the alkene followed by beta-hydride elimination regenerates the catalyst and leads to the formation of the vinyl silane product. Also, the groups of Zhang and Shao reported a carbon-silicon-silicon-hydrogen metathesis of aryl hydrosilanes to access diaryl silanes under Lewis acid catalysis. In here, the formation of volatile dimethylsilane as a byproduct was postulated as the driving force of the overall reaction. Previously, we have mainly discussed processes in which either the same bonds or substituents across an X-H bond were exchanged. This ultimately means that a hydrogen atom is exchanged with a functional group and vice versa. A potentially attractive alternative would be to develop functional group metathesis reactions wherein two functional groups can be interchanged. One key advantage compared to traditional functional group interconversion is that the interconversion can be carried out in both directions under roughly similar reaction conditions. An example of a functional group metathesis process was described by the group of Morandi. They demonstrated that under palladium catalysis, aryl iodides and aryl chlorides can exchange their iodide and acid chloride functionalities. The reversibility of this process was demonstrated through a simple control reaction wherein either iodobenzoyl chloride or iodobenzene and decarboxylic acid chloride were subjected to the standard reaction conditions. This resulted in the formation of an equilibrium mixture of all three possible products. Having demonstrated that this reaction is reversible, procedures to access aryl chlorides from aryl iodides and vice versa were developed. A central problem is the requirement to identify a suitable driving force to ensure good conversion towards the desired product. Either a sterically congested or electron-deficient aryl chloride was employed for the transformation of aryl iodides into aryl chlorides. For the reverse transformation, iodobenzene could be used in excess, or an electron-rich aryl iodide, which leads to the formation of a push-pull stabilized aryl chloride, could be used to drive the reaction. Simultaneously, The Arnsten group also reported a palladium-catalyzed aryl chloride-aryl iodide metathesis. They found that electron-deficient aryl chlorides were suitable COCl sources for the metathesis to enable a CO-free pathway to aryl chlorides. More recently, the Morani group demonstrated the metathesis between aryl nitrile and aryl thioethers under nickel catalysis. Notably, these two functional groups are complementary in terms of their reactivity and, for instance, their directing ability for aromatic functionalization chemistry. To efficiently shift the equilibrium to either side, either electron-poor 4-cyanobenzoate or 1,4-dicyanobenzene were used as nitrile donors, or electron-rich 4-methoxythioanisole or 4-morpholine thioanisole as thiomethyl group donors. Subsequent mechanistic investigation showed that after oxidative addition of the nickel catalyst into the aryl nitrile or aryl thioether bond, transmetallation can occur, leading to interchanged aryl nitrile or aryl thioether products respectively. Interestingly, they could also show that in a non-productive pathway, the nickel catalyst can oxidatively add into the CsP3 sulfur bond. To avoid this undesired reactivity, an improved protocol was developed using sterically more demanding alkyl substituents on the aryl sulfide. Thus, the catalyst loading could be reduced. Besides providing novel routes to important chemical products in organic synthesis, the application of reversible reactions has also been exploited in other fields of research, for instance in asymmetric catalysis and more specifically in dynamic kinetic resolution. Kinetic resolution describes the use of a chiral catalyst or reagent to promote a selective reaction of one enantiomer in an achiral reactant mixture. One drawback of this strategy is that a maximum theoretical yield of 50% can only be reached. Therefore, the concept of dynamic kinetic resolution was developed, allowing the concurrent racemization of the starting material while a kinetic resolution is performed. Thus, theoretically, 100% of the racemic mixture can be converted into one enantiomer. Often, fully reversible reactions are implemented to facilitate this racemization step. Coming back to transfer hydrogenation reaction that we have discussed at the beginning of this session, a chemoenzymatic dynamic kinetic resolution of primary amines was realized by the group of Beckwell in 2005. The key racemization step was facilitated by the Schwarz catalyst. The racemization occurs via a combination of dehydrogenation of the chiral amine and re-addition of the hydrogen to the imine intermediate. Subsequent acylation mediated by the lipase relying on isopropyl acetate as the acylating agent in combination with sodium carbonate affords then the optically pure products. To sum up, reversible reactions have not only been useful in the context of dynamic combinatorial chemistry and material synthesis, but also have been utilized in synthetic organic chemistry to access more functionalized or enantiomerically enriched products. The conceptual realization of shuttle catalysis and metathesis reactions enabled the implementation of safer protocols, as for instance the use of hydrogen gas or toxic hydrogen cyanide could be avoided by the development of transfer hydrogenation or transfer hydrocyanation protocols. Overall, also novel reactivities could be established based on these principles, as for example showcased in the dehydrocyanation reaction of aliphatic nitriles to access alkenes. Thank you all for joining the session, and if you have any further questions or comments, please feel free to contact me by email or LinkedIn.
Thank you once again, Julia, for a very nice talk on reversible reactions. We will continue our module on synthesis in our next lecture as well, so feel free to check that out too. And see you next time.